All right. Okay, our last section of chapter 13. Section 13.4. This section is called language recognition, though we did already define what it means for a finite automaton to recognize a language. This is just going to go into a little more detail about that, and we're going to dive into some sort of theoretical stuff. The big question we want to ask here is what kind of languages can be generated / recognized by finite state automata? Implicit in that question, although not necessarily, but implicit in that question is that it's not all of them. And indeed, that turns out to be true. Finite automata can't generate all possible languages. They're limited in what they can do. So they're not the only type of finite state machine. I want to make that clear. Finite state machines come in lots of different shapes and sizes and types. And the textbook in 13.4, later part of 13.4, does go into some other types. Right at the end, it talks about push-down automata, linear bounded automata, and then the sort of ultimate finite state machine known as a Turing machine, which is like the ultimate computation model. Kind of mentions that. I'm not going to go into that, but one of the teams is going to be giving a presentation about that. So when you all post your presentations, I encourage everyone to check that out. Turing machines are awesome, in my opinion. But I will leave it to that group to tell us how awesome they are. So back to finite automata. The question of what kind of languages can be generated by them was answered by a fellow named Stephen Kleene back in 1956. Stephen Kleene is the one who developed the clean closure operation named after him, and he also has this famous theorem, Kleene's theorem, that we're going to be looking at today. And the answer is that the type of language is a type of language called a regular language. Or the sets that can be recognized are regular sets. Okay, regular sets or regular language, it's kind of the same thing, since a language is just a set of strings. Now, that's a very unilluminating answer because Stephen Kleene just made up that terminology for the type of set that can be recognized by an automaton. So, what is it? Well, we're going to define regular sets recursively as follows. First, our base case. The simplest sets that are regular are the empty set. So, the empty set is regular. It's possible to have the empty set be a language, right? It's a subset of the set of all strings over any alphabet. So that's a regular language. The set containing just lambda by itself is regular. And then the set containing any single element from your alphabet is regular. So I'm going to write that as the set containing A is regular for all A in whatever our input alphabet I is. Okay? And so that's our base case. But then we will define the set of regular sets, or the class of regular sets, recursively with a recursion rule, which says if A and B are two regular sets, then so are A concatenated with B. We defined that in the previous section, as well as A union B, and the clean closure of each of them, but we'll just say the clean closure of A. It might as well be B without loss of generality. So essentially this is saying those three operations on sets of strings that we defined in the previous section, in the previous video, if A and B are regular sets, combining them or doing a clean closure of one of them produces a regular set as well. So those are the operations that you can do. And anything that you can achieve via combinations of regular sets using those operations is still regular. So that's the definition, and that's the answer to what types of languages a finite automaton can give you. Now we're going to look at an example of a language which is not regular shortly, but that'll be in the next video. For now, I want to finish this video by introducing what are called regular expressions. So regular expressions are just a shorthand for representing regular sets. And in the textbook, they use bold in place of regular text, and I'm going to use my blue pen here to represent bold. So first, for these three base case sets, we use bold. This one is kind of stupid because it's the same thing. But regular expressions are often represented by, with bold. So bold empty set just means the empty set. But bold lambda will represent not lambda itself, but the set containing lambda, which is slightly different, right? So make sure you're aware of that. And then bold A, or any other bold character from the vocabulary, will actually be representing the set containing that character, like that. And so then you can do things like, for example, X, Y, union 1, parentheses, star. And something like that would mean, that would be an example of a regular expression where you're saying take the element X, concatenate it with the element Y, and then take that set union with the singleton set containing 1, and take that whole result, and then take the clean closure of that. So this looks a lot like just algebraic expressions using plus, times, and powers. And it's very similar to that. So regular expressions just sort of establishes a notation to write things down more easily without having the curly braces all over the place. So I just want to finish this video by zooming in on one of these tables here. It's got a few good examples. Let's see. Yeah, take a look at that table 1 there. So in this case, we're dealing with Boolean set 0, 1, and each of the bold 0, 1s represents really the singleton set. So what this means, 1 concatenated with 0 star. As you might expect, there's a precedence of operations, like an order of operations, and the clean closure, like exponents in a way, takes precedence over other operations. Concatenation is like multiplication. It takes precedence over union, which union is kind of like, playing the role of addition, right? So that's the order of operations. So this would be saying, take the clean closure of 0. That's essentially a string of zeros of any length, possibly none, length 0, all the way up to length whatever high number you want. Not infinite, though. And then, so 1 followed by a string of zeros. That's all it is. And then, whereas if you put parentheses around that 1, 0, now that overrides the order of operations. And so now what we're saying is take a string which is made out of copies of 1, 0, the string 1, 0. That would include possibly no copies, which is the null string or empty string, lambda. So lambda would be in that language, but not in the first language. The third one here is just contains two things, 0 and 0, 1. And then the fourth one down is interesting because it starts with a 0, right? So this, in order to be in this language, it has to begin with a 0. But then the 0 or 1 gives you the entire input alphabet. 0 union 1 gives you both. And then taking the clean closure of that means essentially any string of any length over that alphabet. So if you take away the 0, that right there represents all possible bit strings. Put the 0 on the front, and basically it's any bit string beginning with a 0. So there you go. The last one is quite difficult to wrap your head around, though. Here we're saying essentially chunks of this format, 0, star, 1, and then take the clean closure of that, which would be any number of concatenations of strings of that format. And what this basically means is that we can have any number of zeros, including possibly none of them, and then a 1, and then any number of copies of that format, which all this does is it forces the final bit to be a 1. Because these chunks always end in a 1. They could have zeros preceding that, but they always end in a 1. And that is what is being designated here. There's no other restrictions on that besides that it has to end with a 1. So it's described here as any string not ending with a 0. Sure. There is a distinction there, I guess. The empty strings, that is, is in this as well, because the entire thing is a clean closure. So that would make the empty string a possible element of that language. So not ending with a 0 is slightly different than saying that it has to end with a 1, because this would also include nothing, empty string. So there you go. That's regular expressions. Now, I want to say that regular expressions have some neat applications. If you are running a search through a Word document, like if you're in Microsoft Word or if you're on a web page and you hit Control F and you search for something, right, some string of characters, regular expressions can be used to do that sort of pattern matching. The regular expression can like represent a pattern, and then what you can do is search through a document for strings that match that pattern. So a finite automaton could be essentially like when you type in search for the pattern ABC, then it's like you could build a little finite automaton that would specifically search for the pattern ABC. And that's possible because it's a regular expression, and regular expressions describe regular sets, which are exactly the types of sets that can be recognized by finite automata. So that's kind of the connection here. This has applications in that sort of pattern matching, search engine type fields.